In the last few segments, we talked about stereoisomers with a focus on recognizing molecules that are related as enantiomers, picking out chiral centers within molecules, and assigning those chiral centers as R versus S, as well as recognizing that the D and L forms of molecules are related to one another as enantiomers. Here in this video, we set the stage for our future work in evaluating the stereochemistry of carbohydrates by talking about how to go about drawing so-called Fischer projections. First off, I have not misspelled the word Fischer here. We're not referring to fishing here. Instead, we're referring to a scientist named Emil Fischer. And Emil developed a simplified system for drawing isomers that show the arrangement of atoms around chiral carbons. He ultimately received the Nobel Prize in Chemistry for his work on carbohydrates. Now, this particular model that we use is referred to as a Fischer projection, and it's a simplified way that we can represent the stereochemistry of carbohydrates or sugars. In this particular type of model called the Fischer projection, we are going to make some abbreviations and assumptions about how atoms are oriented in space and what that means in the way that we draw these so-called Fischer projections. To begin, we will use lactic acid as our example molecule to illustrate how we go about drawing a Fischer projection. We also have in the top half of the panel here a rather generic schematic of ball and stick models of a chiral carbon, where the chiral carbon is in black, and we represent the 4 different groups bonded to it, numbered here 1, 2, 3, 4, as the 4 different groups bonded to the chiral carbon. In a Fischer projection, what we do is we reorient this tetrahedral carbon atom so that when that is reoriented, it's set up so that the carbon that's chiral is in the center. 2 of the bonds point toward us as wedges, and those are oriented horizontally like we see here. And then vertically, the bonds are dashes pointed away from us. So the chiral carbon looking vertically on the spine here has bonds that are pointed away from that chiral carbon. Horizontally, the bonds are pointed toward us. And to simplify that even further, what we do is we take that and simplify it into simply lines, where it's implied here that the horizontal lines represent wedges and the vertical lines represent dashes. So even though there's no wedges and dashes shown here, it's implied in this so-called Fischer projection that horizontal lines equal wedges relative to the chiral center that's in the middle there. Vertical lines represent dashes or bonds that point away from the chiral carbon that is in the center. And this carbon here is our chiral carbon by definition. So applying that toward lactic acid, specifically this is S-lactic acid here, as we learned in the prior video to assign chirality as R versus S. We view from the perspective of the chiral carbon here, and what we do in orienting this is we place the molecule with the COOH oriented upward on a dash. Following the longest carbon chain, we put this CH3 down here on a dash, and then the H and the OH are represented here and here. Now, to simplify that out as a Fischer projection, we come over to here, and we've drawn everything as simply straight lines, where these wedges are defined as straight horizontal lines, vertical are defined as dashes. Now let's apply the foundations of Fischer projections toward some simple sugar molecules such as glucose. Particularly, the structure that we see here is D-glucose, and we're going to decipher why we would refer to this as the D stereoisomer, as well as some general features of this molecule. First off, when we are drawing Fischer projections of sugars, what we're going to find when we get into sugar molecules is that sugars generally have several carbon atoms that are chiral, and you will also observe generally that within a sugar molecule, the carbon atoms are in multiple oxidation states. Generally, when drawing Fischer projections, we orient the molecule vertically. So in other words, the longest carbon chain within the molecule is oriented vertically, such as is the case here where our longest carbon chain coming through the spine here, where each intersection represents a carbon atom, we can confirm that this glucose is a 6-carbon molecule, starting with the aldehyde group and coming through with each of these intersections represented carbon, finishing with the CH2 down here. We orient that carbon chain vertically, like we have here, where the vertical spine of the molecule would be all those bonds that are dashes, and horizontal here would be bonds that represent wedges. Moreover, the most oxidized carbon atom, the aldehyde group in this case CHO, is oriented at the top of the molecule. So our most oxidized atom, by convention when drawing Fischer projections, is at the top. So don't flip this around, put CHOH up here, put CHO up here. So the most oxidized carbon atom will be at the top of the chain there that I've highlighted and written out here in red. And then the intersections generally represent chiral carbons. So I can go ahead and put stars on these here, 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 and here. Each of those represent for us a chiral carbon because each of those carbons has 4 different groups bound to it. Here at this carbon we have an OH group, an H, an aldehyde, and then the rest of the carbon chain. Here we have an H, an OH, carbon chain here, and carbon chain here. Those 2 groups are not identical as we look further down the chain. Coming down this one, we have an aldehyde group. Coming down this way, we do not. So that represents a chiral carbon. We could do that at these additional 2 spots as well, recognizing that the structure of D-glucose has 4 chiral carbons if we were asked that question. Now, within this, one question that arises is how do we say that this is D-glucose? What information, if any, is there in the chemical structure of this that tells us this is D-glucose, that it would rotate light in the counterclockwise direction? The way that we tell that this is D-glucose and not the enantiomer so-called L-glucose is based on the orientation of this hydroxy group. That is, the very last chiral center's hydroxy group is what allows us to establish whether this is D or L. At this final chiral carbon, if the OH group is on the right, then the molecule will rotate light clockwise and be described as the D enantiomer. On the other hand, if the OH group pointed to the left at this position, we would describe the sugar as the L configuration, so it would be L-glucose. In this case, definitely D-glucose because the OH group here is on the right. What we will see when we get into our unit in more depth on sugars is that we will see a wide variety of sugars that all have a skeleton analogous to this, but differ in terms of the stereochemistry at each of these chiral centers, leading to a variety of different biological functions of sugars and the need to be able to draw these with the shorthand Fischer projection notation. So we will get into Fischer projections at a deeper level as we continue on, but for now, what you need to be aware of is what we have looked at here. You need to be able to assign the configuration as D versus L based on the orientation of this very last chiral carbon here, where the molecule is oriented starting from the most oxidized carbon and then down the chain here. This very last position hydroxy group is what drives whether it's D or L. Recognizing that these intersections here usually represent chiral carbons, and they definitely represent carbon atoms. We orient the molecule with the chain vertical, and the most oxidized carbon atom is at the top by convention. And in these Fischer projections, any of the bonds that are horizontal would be represented by wedges if we were actually making a 3-dimensional model, and everything that's vertical would be represented by dashes in a 3-dimensional model. So stay tuned for applications of these Fischer projections as we look in more depth at the different types of sugar molecules and how these considerations of stereochemistry or 3-dimensional shape play into the biological roles that sugars play.